Well, good morning, everybody, or good afternoon, or good evening, depending on where you're located in the world. This is Gene Bohensky, the Director of Application and Partner Learning at Perma. And the title of this webinar is How Perma Systems Reduce SEMS Operating and Maintenance Costs. And this has some new slides and some revisions that we've added to this presentation to make it a little bit more educational. So if you've seen it before, I hope you enjoy the new version. As an introduction, for over 40 years, Permapure's Nafion gas sample dryers have been successfully designed into a wide range of SEMS and analysis equipment and are used in many scientific experiments. Particularly with SEMS, we have over 30 years of experience building our dryers and developing sampling systems for SEMS systems. So we have a long history in this field. And the main application is the replacement of the desiccant or the Peltier or compressor gas cooler to solve water problems. Specifically for SEMS, we're replacing the cooler. Permapure is the world's only manufacturer of Nafion tubing. And this presentation is going to cover 3 parts. Number 1, the unique benefits of Permapure systems for SEMS. Number 2, how Permapure systems work. And number 3, additional solutions to improve reliability of cooler-based systems. So let's get started. Unique benefits of Permapure systems. Our Nafion-based sample conditioning systems for cold extractive and other SEMS have a number of very important benefits. And we're going to focus on these benefits in this presentation. The first one is that we could measure low-level SO2 and NOx accurately as required by new standards being implemented worldwide. We can slash installation, maintenance, and operating costs of any SEMS system. We can increase those systems' reliability and solve common application problems. And as we call it, Permapure SEMS systems is a proven solution for SEMS sample conditioning. So let's take a look at where we play here. This is a typical diagram of our application here from a smokestack found in a refinery, power plant, wastewater treatment plant, any type of manufacturing plant. We have a probe that is designed to extract a gas sample from the exhaust here or the effluent. And we are bringing that into the sample conditioner that prepares the sample for the analyzers. Now, the samples coming off the probe are dirty, wet, and hot, and they need to be cool, clean, and dry for the analyzers. And so the job of the sample conditioning system is to prepare that sample for the analyzers. And that's where we play, the probe and the sample conditioning system. So let's look at the main SEMS measurement methods that are out there. The first is the direct extraction method. That's where we mostly play, where the sampling probe extracts from the flue the gas and transmits it with the heat and the dust and all that stuff into the analyzer cabinet. And the system is designed to prepare that for analysis. And you also have 2 different ways, either IR or infrared absorption spectroscopy technology or ultraviolet absorption spectroscopy. Okay. That is the UV absorption is where you can do it hot and wet. There's also the diluted extraction method where you have a dilution probe. And there the principle of measurement is ultraviolet fluorescence for SO2 or chemical luminescence for NOx. And then there's a direct measurement, directly install on the meter on the flue and test the components in the flue gas. That's the in situ. There you use ultraviolet absorption spectroscopy or tunable laser technology. But for the most part, we're working with a cold extractive SEMS, which has proven to be very reliable and cost effective over time.
Using this existing validated sample.
So let's look at the way this setup is supposed to work. So At first, you have the probe and stinger. The stinger is what actually points into the stack. You stick it into the stack and you allow extraction of the sample gas at the appropriate sample sample location. This is where you have your first point of filtering sometimes, or ideally. You have a blowback system, so you have the ability for compressed air to compress and blow back a blast of gas to clean the filter, blowing the particles back into the stack. That's why it's called blowback. And this stinger and probe should be heated to prevent condensation. Typically, the dew points of the gases coming out of the stack can be as high as 70 degrees C. And we need to keep the sample above, you need to keep the probe and the whole sampling line way above that dew point in order to prevent condensation. You also then have the heated line, which transports the sample gas to keep it in the gas phase. Recommend at 120 degrees C or 180 degrees C until the sample is dried later on with the sampling conditioning system. One of the reasons why you need to go so hot is that not only do you have the dew point, the water dew point, but you also have an acid dew point. You also have the point at which acids can condense, and that's usually above 120 degrees C or thereabouts, depending on your stack gas. And if those condense out, that's a real issue. That's a real problem because they can create all kinds of havoc down the line because they're very acidic and very sticky. Then after your heated line, you have your sample conditioning system that removes the moisture that allows the cold and dry gas analysis. It also removes particles and acid mists and other things you don't want. And it should not remove the analytes that you do want. So you should be able to take out the bad stuff while keeping the good stuff, that is the things you want to measure. And then of course you have the analyzers, which are either multi-gas analyzers or multiple single gas analyzers. Each analyzer typically takes 1 liters per minute of sample gas. So if you have multiple analyzers, you have to increase the sample rate coming down from the stack. Gas analyzers do not like liquid water inside. This will result in analyzer failure, which is why it's so important to be able to reliably take out that moisture from the sample gas. You also have calibration gas, which needs to be used on a regular basis, depending on where you are in the world. Some people have to do daily calibrations or calibrations on a regular basis. What that does is it compares what you're actually measuring, and you're making sure that your sample is being measured accurately. So you take a measurement against the calibrated gas to make sure it's accurate, and that whatever is coming off the flue will be measured accurately. Then, of course, you have data reporting, which is required for the local authorities. It's different depending on where you are in the world, to be able to certify that your plant is running within the parameters set forth by the local authorities. This is the lowest cost method with proven technology. So cold extractive SEMS is reliable, it's a known, people have been doing it for many years, and we've all developed a lot of experience with cold extractive SEMS. So here's some of the unique challenges of SEMS and these type of applications. In general, they have high operating and compliance costs, and it's important to understand these just are presenting costs for the end user. They're not getting any profit out of this. So the thing that the most end users want to do is reduce those costs, because it's not helping them. It's not helping their process. It's not helping anything. It's just a cost of compliance, the cost of doing business. There's also difficulty of sampling hot, wet, and dirty and corrosive samples reliably and consistently. So we talked about cold extractive SEMS, but some of these other methods that are newer, using in situ analyzers, where you're actually analyzing it hot and wet at the stack level, or you're bringing down the sample hot and wet and you're analyzing it without conditioning it. A lot of those more advanced methods, in order to get rid of the sample conditioning, have introduced their own challenges. Some of them are unreliable. Some of them need to be cleaned on a regular basis, because the reality is it's not easy to sample hot, wet, and dirty and corrosive samples. It's just not easy. You have a high reliability required. The systems must run for a long time without supervision. Again, it's a cost center. It's not a profit center. So the systems must tolerate adverse and faulty operating conditions. Operating conditions sometimes change at plants if there's a challenge, and you want to make sure the sample conditioning system can handle that. You also have the possibility of operating in hot and humid ambient conditions up to 50 degrees C, installed outside. Traditional systems require high maintenance with frequent and costly repair and upkeep to maintain compliance. So here's some specific limitations of cooler technology. Coolers are the ones, this is the technology that is most often used, primarily because of the low cost, low acquisition cost. But coolers are easily overwhelmed if the flow rate and sample gas conditions change. This is because they have a very narrow range of operation depending on how they're specified, and they really can't go over that too well. You also have a likelihood of catastrophic mechanical failure, which equals expensive damage to analyzers. So coolers fail, like a lot of electromechanical devices. When they fail, they will fail catastrophically. That's just normal for those that type of equipment. It's just what it does. You also have an operating dew point of +4, which is what they cool to. It does not remove all the corrosives, which can condense and collect on the analyzer optical bench over time. So it still allows enough moisture and enough of the gases that make it possible for acids to collect ahead of the cooler. And the coolers require air-conditioned enclosures to operate above 40 degrees C, increasing installation costs. You also have high SOx and NOx losses from the condensing design that lowers accuracy or makes practical measurements impossible. So, of course, the challenge here, what you're doing with a cooler, is you're condensing the water out of the sample stream. This is in contrast to Nafion, which removes the water in the vapor phase. And when you condense the water out, you're going to lose any of the components that are soluble in water. There are some manufacturers that are promoting phosphoric acid doping that is promoted as a way to improve accuracy, but it's tricky, impractical, and unreliable. It needs a lot of hand-holding to make sure that your phosphoric acid is enough. You have to constantly watch the system. It is really not a practical alternative. So the solution is Nafion-based sample conditioning systems, the proven solution for SEMS. So the key technology differentiators with our systems is, number one, we measure SO2 and NOx accurately by eliminating the potential for analytes to dissolve in the condensate. Number two, we slash operating costs from removing water in the vapor phase and drying the gas to a lower dew point. This has many benefits we'll describe later on. We increase system reliability from the elimination of the potential for catastrophic mechanical or electromechanical failure. We reduce costs further by mounting the system on the stack to eliminate the heated line and drop calibration gas usage. And we can add ammonia scrubbers to further cut costs if you're working with any systems that have ammonia in the gas. The result is that Nafion systems can pay for themselves in as little or less than 12 months. Let's look at some of the methods of dehumidification. We have on the left a semiconductor chiller that's like ours, our Baldwin series. We have a lot of experience with coolers because we make them ourselves. Here's a compressor-based cooler there in the center. And then on the right, this is a Nafion-based sampling system, one that we make. So let's go to what Nafion polymer is. So what is Nafion? So Nafion is a copolymer of Teflon and sulfonic acid and is highly resistant to chemical attack. Nafion polymer removes water by a first-order kinetic reaction in the vapor phase, so equilibrium is reached very quickly, typically within milliseconds. The transfer of moisture is driven by the differential water vapor pressure between the membrane sides. And the Nafion polymer permeation selectivity is based on the chemical reactivity of water with the membrane. It's not traditional permeation, it's not based on size. And this diagram at the right shows you how it works. So in this diagram, you have the flow moving from right to left, coming out of the tube. You see the blue spheres in the tube, and outside of the tube represent the water being removed from the sample gas. And what's left over is the red, green, and yellow components. Those are the ones that you want to measure. So the way the water is transfers through the material is unique. It's what makes Nafion unique is that it is a chemical reaction with the surface, and then the water becomes part of the material's structure, and the water moves through the lattice, through the material, from one side to the other, based upon the relative vapor pressure differential of water. Okay, and so it's also not traditional permeation. So with traditional permeation, it's kind of like a bug screen, where you have a screen with holes in it, and the holes match the size of the molecules that you want to move through the screen. That's not what Nafion does. Because the water, it actually becomes part of the material's chemical structure. Because of this, no energy is required. It just works on a differential vapor pressure, and it's highly efficient, and it happens very quickly. But why is Nafion polymer selectivity so valuable? Why is it so important for our industry, right? So the reason why is that only compounds that chemically associate with sulfonic acid permeate through Nafion polymer. Because this is a specific chemical reaction with water, the process is very selective, and many gases being dried are entirely unaffected. Now let's take a look at these gases in red here that I circled in red. These are precisely some of the gases that are so important for us in the SEMS world and in the process emissions world, because our customers are looking to measure these. And it is precisely these components that Nafion leaves alone. That means we can remove the water from gas streams that include these components without affecting these components. And that is so important for industry, and that's why our whole company has been so successful over the years, because we've been able to exploit this very favorable property of the material that has become so valuable. So if you're doing any kind of analysis with atmospheric gases, halogens, hydrocarbons, inorganic acids, other organics shown there, oxides, any type of sulfur, or toxic gases, a PermaPure Nafion polymer dryer will remove the water while keeping those components intact. It's very important to understand that this is what makes Nafion the ideal material for SEMS and why it's proven so effective. The other part of it also is that because it's based on Teflon, it is also totally chemically resistant to any of these compounds as well. So not only do you have the ability to remove water without affecting those compounds, the material is very corrosion resistant to any of the type of nasty gases, nasty corrosive gases that come off a smokestack. They're not going to affect or corrode the Nafion tubing. So let's go to the next major benefit, which is the consequences of drying SEMS samples to a lower dew point in the vapor phase. And we think this is a big reason why we drastically lower SEMS maintenance and operation costs. As I pointed out to you before, a cooler can really only get down to chilling or cooling and removing water to a dew point of +4. But with a Nafion-based dryer, we can get down to -15 or lower. And that means a couple of things, and we do that in the vapor phase. So the loss of water-soluble analytes, SO2, NOx, we don't lose those analytes. So we could make accurate measurements under 50 parts per million. Many of the new areas in the world are requiring very low rates of SO2, whether it's a marine SEMS or in other countries such as China. Like we have a lot of experience in Southern California and other places that are deciding to limit their emissions. The only way you're going to really make accurate measurements is by using a Nafion tubing dryer in your SEM system. They also protect analyzers. So we've reduced the amount of acid mist that condense on the analyzer optical bench. This is very important. I'll show you in another slide how we eliminate over 80% of the water left behind by a cooler. And this makes it a lot less possible for acids to form ahead of the cooler. So we eliminate the potential for damage to the analyzer or system components. We have the potential to solve many application issues stemming from the presence of water. We also have reduced interference in infrared or other measurements because a lot of times the water interferes with the peaks given by the other components in those measurements. And we also reduce or eliminate clogging of line or system components. So here's a couple of unwanted chemical reactions that we can eliminate here. So the first is the formation of sulfuric acid. These cause problems in the sample lineup for the analyzer. This is where you have your SO2 plus oxygen combine to form a 2SO3. When you have SO3 and water together in the vapor phase, you can get H2SO4, hydrochloric acid, okay, or sulfuric acid. This is very important. This is what we reduce when we reduce the vapor in the gas stream. We also have the potential to do it in this way too. NO2 plus SO2 plus H2O gives you the sulfuric acid plus NO. This also changes your readings as well. So this formation of sulfuric acid is reduced if we can eliminate that water coming out of the cooler, the water vapor coming out of the cooler. Then you can also have the formation of ammonia salts if you have ammonia in your sample stream. Your ammonia plus SO2 and water gives you NH4HSO3, and you can also form NH4HSO4 when you have SO3. These ammonia salts have been known to plug many sample lines. So here's your water vapor saturation pressures I want to talk about a little bit. The first level is for a wet scrubber system coming off of a typical nasty system. You're up to a dew point of 70 degrees C in your stack, which is about 30% water. These can typically overwhelm a lot of cooler-based systems, but our Nafion gas sample systems can handle 30% water without much trouble. The next level down to talk about is the water vapor present in a natural gas combustion stack. You typically have a dew point of 46 degrees C or 10% water vapor. A typical thermoelectric cooler outlet dew point gets you to about 4 degrees C or 0.8% water. That's typical. And look at the bottom there. A Nafion dryer system, typically at minus 18 degrees C dew point, will get you a percent water of 0.12, removing over 80% of the water left by the cooler. This is one of the reasons why you have so much less problems with your analyzer and much less analyzer maintenance, because we don't have that water vapor in the sample gas that's going to recombine with the components that we're looking to measure to create acids. So let's look about water damage to analyzers. During certain conditions, coolers may not be able to react quick enough to incoming gas samples. If the gas is not fully condensed or the cooler fails entirely, liquid condensate is likely to leave the cooler. The corrosive condensate will land on the optical bench of the analyzer. Repair will cost $30K and will require a few months. A Nafion system prevents this occurrence by offering a higher drying capacity and a greater fault tolerance. And the outlet dew point is much lower than coolers, as I mentioned before. So this is the real reason why why Nafion tubing dryers save money for SEMS operators, because these conditions can occur, and over time, if you're running multiple sites, we have a system integrator that actually builds in Nafion gas sample dryers ahead of the coolers as a preventative measure, and they found that the coolers pay for themselves. They've done the statistical analysis and show that they prevent damage to the analyzers enough to make it worth putting them in addition to the coolers, not just instead of. So let's take a look at how Nafion dryers work. They are a simple tube and shell design that functions with water vapor similar to how a heat exchanger transfers heat. As you can see in the diagram, the sample gas flows through the inside of the tube from left to right, and the purge gas flows in the opposite direction from the right to left. The flows are sealed off from one another so they don't mix, and that purge gas is what removes the water, strips the water from the sample gas. It is available in a wide range of dryer lengths and tubing diameters, basically to match the amount of water in the sample stream. And the materials are in polypropylene, fluorocarbon, and stainless steel, depending on the corrosion resistance required by the tubing, or by the sample gas. So let's take a look at our PD series here. That's the type of dryer that we build into our systems. Those are shown there on the right. It's similar to the other one, but the difference is we have multiple tubes in parallel. The thing I want to talk about these is that we have no catastrophic failure mode in these dryers, which is very important when you compare that with electromechanical or electronic systems. What happens over time is that they might get fouled with some dirt over time, but the performance will never drop instantly from one level to another. The multiple tubes in parallel increase the flow rate capability and efficiency. We have final dew points that can be as low as -15 to -25. The dryers are corrosion resistant and rugged, making them long lasting and tolerant of very harsh samples. We have flow rates to 20 liters a minute and pressures to 80 PSI. Again, no routine maintenance required, reliable and easy to operate. And this is really the most common dryer used with SEMS because of the flow rates. I'll show you again how Nafion dryers have a high tolerance for changing and challenging conditions. Let's take a look at the green curve. That's a 24-inch dryer. And let's say we have a PD50T. So this is the top line of the performance. Let's say we're at 5 liters a minute. You could see that at 5 liters a minute, you're getting to a dew point of roughly -8. But what happens if your flow rate goes up to 8 liters a minute? Well, your dew point goes from -8 to -5, not that much of a difference, right? There's a high tolerance, and that's equivalent to doubling the amount of water in a sample. In fact, you can go to this 10 liters a minute number at the end. Your dew point is still -4. If you double your flow rate from 5 to 10 liters a minute, your dew point goes from -8 to -4. So what you're seeing is that you could double the flow rate. That means doubling the moisture being put through the dryer. You could see that that the dryers have a high tolerance for changing conditions. That means the dryers aren't going to spit out water and send water to the analyzer bench if optical bench if there any problems occur. It's very important to understand that. And here's the consequences of drying in the vapor phase. You could see the sulfur dioxide solubility in water here. You could see that the solubility is high at about 70 here, 70 milliliters SO2 here at this section where you're at 4 degrees C, you could see that the solubility in water is the highest where the coolers operate. So by drying in the vapor phase, you eliminate this entirely, and you're able to leave the SO2 content intact. So here's a further benefit: where to mount the sample conditioning system on the stack. This gives you a further huge reduction in installation and maintenance costs by the elimination of the heated line. By drying and treating the sample gas at the stack, you are now transporting dry sample gas, so the heated sample line is no longer required. The savings: heat trace sample line at $30 to $60 per foot can be replaced with freeze, protect, or simple multi-line umbilical at 1/4 or 1/3 the cost. Total savings depends on the sample line length, but from $50,000 to $30,000. In fact, the savings can be even more than what the system costs itself. That's what a profound impact that this makes. Further, huge reductions in installation and maintenance costs come from the elimination of anything that will clog the line or system components. We eliminate unwanted chemical reactions downstream of the sample system. So we never have the potential of stuff gumming up in the sample lines. As you might well know, sample lines are not the most reliable systems in the world, and a lot of times the reason why you get clogging is because somewhere along the line, the sample line, the heated line fails, and it doesn't heat all the way through. You also have shortened response time due to adsorption and desorption, greatly reducing the amount of calibration gas that is being consumed. Now, this obviously depends on whether and how you're putting together your calibration. In the United States, we've got to put the calibration gas directly in the sample line up at the stack and read the calibration gas from there. But in some places in the world, you're able to input the calibration gas directly at the analyzer and do that calibration. So it's a little bit different depending on where you are. So here is a typical cold extractive roadmap, a typical configuration. You have your probe and your stack, you have your heated line. Your heating line goes to a condensing cooler. Here you have your sample, your calibration gases, and here's your analyzer rack, and then your data goes to your computer. Here's a cold extractive road map with PermaPure's probe mount. Okay, so here we have our probe here mounted on the stack. You have your sampling conditioning system right at the probe, in fact, together with the probe. And then from here, you have your unheated freeze protect sample line coming out for your analyzer rack. In this case, we are taking our calibration. It's done at the probe instead, which gives you a much more accurate calibration. And the sample gases or the calibration gases are put through the probe and then through the sample conditioner and into your analyzer rack. That's the difference. So let's do a summary of why Nafion membrane technology is ideal. Number one, by Nafion dryers. It is not mechanical and does not require regular maintenance, costs marginally more, able to measure low SO2, does not require a heated line, it protects your analyzer, and has by far the lowest cost of ownership. Gas coolers are the most common technology. They require more maintenance than membrane dryers. They cost less. SO2 is dissolved in the condensate. A heated line is necessary. They're prone to catastrophic failure and prone to water shots or condensate, resulting in analyzer damage. So for the next part of the presentation, this is going to show you how PermaPure systems work and show you how our proven solution for SEMS is really the best solution for any application. Let's take a look at our SEMS tri-zone Nafion management system. So we set up 3 zones where the gas passes through, and each one has its unique place. And I'm going to show you how that all works. So the first here in this is the inside of our gas 2040. And the inside of our system, that we always have two parts. We have a hot area and a cool area. The hot area is where the sample gas coming out of the stack is being processed and being prepared for the dryer. And then the dryer is going to be heated, and that hot, wet sample gas that is now cleaned is going to go through the dryer and exit a cool and dry. So the sample comes in at the center here through the heated filter body. The heated filter body is going to keep that sample in the vapor phase and provide the first level of filtering roughly to 10 microns. Okay. From here, the sample gas goes through this Hastelloy heat exchanger into the coalescing filter. The coalescing filter and this entire area is heated to roughly 80 degrees C, 90 degrees C, depending on the system. And what that does is it keeps the sample in the vapor phase. At the same time, the 80 or 90 degrees C is low enough to condense out the acid mists. So here we're getting rid of the acid mists, and we're also getting rid of all the particulate over 0.1 microns. Well, this is very important because this cleans the sample for the next phase, which are our dual ammonia scrubbers. So if we're on an SCR system and there's excess ammonia slip that is coming through into the sample gas, these ammonia scrubbers are going to strip out the ammonia before the sample is then placed into the dryer. A couple of other things up here in the heated section, we have our blowback accumulator. We have on the bottom, we have a PLC-based system. The PLC controls a couple of things. Not only does it control the temperature of all the heaters, it controls your sample pump if you have a sample pump. It also controls your automatic drain on your coalescing filter, and it also controls the timed blowback. That's on the regular interval that the blowback accumulator is going to shoot out compressed air to clean the filter on the probe. That's all included in one of these systems. So let's go back. Now that we have our clean sample is going into the heated portion of the dryer. So if you've been on previous presentations, you know how important it is to heat the first portion of the dryer to make sure that we remove the water in the vapor phase and we do not have any condensation in that sample stream. Very important. That we not only do we recommend it to everybody else, we obviously do this ourselves by building the heater into our own equipment. Okay, and here we're heating the first part of the dryer to 90 degrees C. So that's zone 2. Zone 1 is the whole area that prepares the sample gas for the dryer. Zone 2 is the portion of the dryer that is heated, that removes the bulk of the water. Okay, and then zone 3 is our ambient lower half. That's where the sample gas in the dryer is chilled and cooled primarily by the purge gas. And the whole area in zone 3 is cool and chilled, primarily because there you have your computers, your PLC, your heatless dryer, your sample pump, anything else that needs to run at a lower temperature for high reliability. That's how our sample systems work. So just to review, in writing, our sample conditioning systems have 3 zones to enable the gas sample dryers to be used effectively for long-term and reliable SEMS applications or operation. Zone 1 is your heated cabinet. Here the sample is maintained at a temperature to prevent condensation. From the probe, the sample flows through a heated 0.1 micron coalescing filter and an ammonia scrubber before the sample is sent to the Nafion dryer. In zone 2, the heated dryer entrance, the sample is flowed through the heated portion of the dryer to maintain the water in the vapor phase, and here is where the bulk of the water is removed. In zone 3, your ambient dryer exit, The sample moves to the second half of the dryer of the unheated portion of the system. It is cooled and polished to the end dew point as low as minus 25 degrees C. The clean and dry sample then exits the system and is routed to the analyzer. So some of the components inside are a heated coalescing filter with drain. This eliminates the routine maintenance. It's a reliable low maintenance device, and it's easy to use with reproducible timing. And here's your automatic filter drain schematic. We also have a heated ammonia scrubber. Here we have a selective reagent. We have phosphoric acid that is placed on ceramic saddles. And what that does is remove the ammonia from the sample stream. And we have our heatless air dryer. This provides a steady supply of dry air. This further conditions the air with the compressed air that is used for the purge gas. Here's our heatless dryer operation. What we're doing, we have 2 cylinders. It's basically a regenerative dryer where we have this timing that times the flow, goes from one to the next. The first flow is where you have the wet gas coming into the left and exiting dry, and then to your dry gas outlet. And then with a portion of that moving opposite to dry the chamber. And then we reverse this, and that starts again in reverse operation. This is designed to dry the air used for the purge gas. So in some cases where that air is not reliable, we can make sure that we have a purge gas that's dry enough to be used reliably. That's an option, although in many cases we put that as a standard item in the gas 2040, for example. So here's our series of systems. We have a wide range of systems available, and basically, just so you know, we pick the system based upon the application. So it depends on what's required for the SEMS. That's how we pick the right system. And I'll show you an application data sheet later on that we provide to our customers, and we help you pick the right system. So our gas 2040 or gas 6000 series have up to 25 liters a minute, very wet gases with blowback and included, and stack mounted as an option. The gas 6000 includes a special humidity sensor. The mini gas 1228 can be used up to 5 liters per minute. There we only build in 1 dryer, but it also has the ability to use an ammonia scrubber. The Indy gas is a lower cost version. It's also up to 5 liters a minute, but no ammonia scrubber potential. The Ready gas is a newer product, also up to 5 liters per minute, but that's designed for emerging markets where no clean instrument air is available. We actually have a system to provide and make its own purge gas, and we're able to use dirty air that isn't very dry in order to make that reliable. We also have the microgas, which is also heated for 1 liter per minute flow rates. That's mostly for process. And we also have the ACEs, which is a version made for ambient temperature applications, also up to 1 liter per minute using reflux vacuum, also for process. The gas 2040 flagship series really does the job with a low final dew point of -10 to really up to -45 degrees C. Non-corrosive components accept high concentrations of strong acids or organics. No moving parts in standard system for low maintenance and high reliability. Flow rates from 1 to 25 liters per minute. Water contents up to 75% by volume. Handles and dries samples that would otherwise overwhelm a chiller-based system. And choose the system based on flow rate requirement and sample gas components. The Ready gas is designed for improved reliability and accuracy, designed to handle difficult situations. It works if your heated line fails. We have double inlet filters with a continuous drain. It works with low quality compressed gas, and it's designed specifically for the challenges found in developing nations. The isolation valve protects itself and the downstream analyzers. It eliminates the high temperature heated line down to the analyzers and enables accuracy when moisture content rises and SO2 levels decrease. It's a very good system for those applications. You could see inside we have dual coalescing filters. It's really designed for these difficult applications. And we have a SEM systems application data form that one of our salespeople can help you with. This application data form helps us protect the select the right product for you. That's what we do at PermaPure. With understanding your SEMS applications, we can select the right product for your needs. Let's just go real quick. The last part of this presentation is going to go over solutions to benefit existing cooler-based systems, lowering costs and increasing system reliability. So the first one is our SDS supplemental drying system we call the Cooler Booster. Basically, what it is two PDs, two polytube dryers that are built into a box. And what you're doing is you're putting the PermaPure tubing dryers in between your analyzer and your cooler. And this protects the analyzer against cooler catastrophic failure. That's the one thing that this does. And the second thing that it does is it lowers the dew point of the sample gas. So you reduce the dew point from 4 to -15 or -20 degrees. It provides a lot of those benefits, a lot of those reliability benefits that I was explaining before, why you can use this and not have to use a cooler. In that this makes certain that if your cooler fails, you always have that last chance drying. These dryers can handle the volume and you won't get a destroyed analyzer. Secondly, you're reducing the amount of water to the point where the water doesn't recombine with those other components to form acids that later on condense on the optical bench. So here is the schematic of the SDS design. One thing I wanted to also say is that we have customers that don't actually buy the SDS, they just buy the dryer itself. But by the way we've created this product, the cost is roughly the same whether you buy the dryer or whether you buy it in the box. So you can also install standard PDs. This was chosen by a major US systems integrator for all cooler installations. Over 300 installations in the United States, it is statistically proven to save money by protecting the analyzers from damage when the coolers fail. This is very important. It is statistically proven to pay for itself and to save money. I think that basically says it all on why these are so important for the SEMS world. The next part and last part is how ammonia scrubbers can help lower SEMS operating costs. And what we're talking about here is installing ammonia scrubbers with coolers, okay? So as we know, the unintended consequences of SCR is ammonia slip, where you have, you use the selective injection of ammonia to reduce the NOx emissions. The slip occurs when unreacted ammonia is released into the flue gas stream. The causes is that added ammonia is never entirely consumed, the catalyst temperatures are not in the optimum range, or too much ammonia is used. Typical ammonia slip can be 1 ppm up to 200 parts per million, with 5 to 20 parts per million a typical measurement. The release of NH3 might not be regulated or even reported. And unfortunately, the analyzer shop does not control the rate of ammonia ejection. Process operators are often not concerned about ammonia slip. And as we know, excess ammonia can damage downstream components in your SEMS systems. Here's some unwanted consequences of excess NH3. You can form acids, like we've shown before. You can form ammonia salts, and you can convert the NH3 back to NO and throw off your readings. All of these are unwanted consequences of ammonia slip. So the solution is to add ammonia scrubbers for coolers. This protects analyzers and downstream components by eliminating ammonia salt deposition. We have, like I mentioned before, phosphoric acid on the ceramic saddles that capture the ammonia. And we have a heated blanket that keeps that operating at a high temperature. And here's your scrubber flow schematic. We have your inlet and outlet on the top, and your sample flows down and then up through the saddles and phosphoric acid where it comes out with the ammonia removed. So there's hot, wet chemistry inside. The target temperature is 80 to 90 degrees C. Ammonia reacts in the vapor form. The water remains in the vapor form, so it fills with liquid, it fills it up, or you can maintain 80 to 90 degrees C in a heated enclosure. The phosphoric acid anhydride reacts with water, then forms ammonium phosphate salts on the inert ceramic. That's how it removes the ammonia. And here's a sample installation with the cooler. So what we want to do is we want to remove that ammonia before the cooler. Some people remove it after the cooler to make sure the ammonia doesn't combine with the water and the other components to form acids on the analyzer. It can be done either way. And here's what a spent ammonia scrubber looks like. Note, scrubber should not be mounted horizontally as this one was. So here's your ammonia scrubber maintenance. We refill media every 40,000 liter ppm hours. So that's the capacity of one ammonia scrubber, 40,000 liter ppm hours. So we can calculate that at a flow rate of 10 liters per minute. With a slip of 5 parts per million, we change media every 33 days. Fortunately, we have customers with such a huge amount of ammonia, they have to change the media every couple days. But that's a challenge. We have a new product called the SAS 3000, which is an ammonia system that has multiple ammonia scrubbers. And basically what we're able to do is put 3 ammonia scrubbers in one system and have a controlled temperature and process in its own enclosure.